the distribution, there's not a great attraction.
Okay, and like, yeah, there's some forces like pushing against because of like the like charges, right?
Like if I drew methanoic acid, it looks a little bit similar to this. You have carbon in the center, two oxygens coming off, but this molecule is no longer symmetrical. On this side of the molecule, there's a lot of electron density. This side, not so much. So now this side has got a lot of electron density, it's a partial negative. So when you have symmetrical molecules, there's no separation of charge, so they don't attract. One last thing I was just going to mention, just as a reminder, if you have a very large nonpolar molecule, it is possible, like if you take butane is a gas, but pentane is a liquid. And the reason why that is that because pentane is so big, and these are all hydrogens on the end that I didn't draw in, because pentane is so big, in fact I'll remove them now, there's enough van der Waals forces between the two pentanes to bring them together to form a liquid. Okay. It's not like they have to be lined up or anything. But this is van der Waals forces, and there's enough force there to bring them together to form a liquid. So even if you're nonpolar, if you're big enough, you can be brought together to form a liquid, and if you're really super long, you can be brought together to form a solid.
How long does it have to be a solid?
I don't know.
It's graphite, yeah.
Graphite is a network covalent, so it's a little bit different because in graphite, there's not a molecule of graphite, it's just this repeating hexon. My guess is you gotta get into like hundreds of carbons long before it would. And also too, it kind of forms a weird state when they're that thick. When do you gotta use the real gas equation? As opposed to the ideal? Under what conditions? So very low volumes and very high pressures. You have to use the real gas equation. But most of the time, if you're dealing at normal pressures and normal volumes, the ideal gas equation will give you the exact same answer as the real one.
What's considered like a very low
Well, it depends partly on which gas you're dealing with, but I mean, you're talking, I don't know, really small. Okay, this would be a good thing to review. Kinetic energy. The average kinetic energy is 3/2 RT. Kinetic energy is 1/2 mv squared. And if you're dealing with the average kinetic energy, it would be the average of your velocities. So that's average kinetic energy.
Is this still chapter 4?
No, this is chapter 5, sorry.
What's the second equation?
This is the equation for kinetic energy. And so when you look at this equation, kinetic energy is
Oh,
related to
yeah,
3
yeah.
halves RT. R is the universal gas constant, 8.31. T is temperature in Kelvin. So this doesn't hurt to remind you. If your gases are all at the same temperature, what did I do wrong?
I'm just confused, like, are those the same but the same?
No,
What's this difference between the second?
I'm just telling you what kinetic energy is.
Yeah, so one
Kinetic
is
energy
like,
is 1 half mv squared.
so
Like,
technically that's
equal to 3 halves RT.
So this is equal to 3 halves RT.
Okay.
I just didn't write it, I didn't put that there because we typically don't use this to calculate the temperature. What they're gonna do is they're gonna give you a graph, and they're gonna give you a graph, let's say, something like this. You could do, we did number of molecules or moles, and then did kinetic energy. And I drew this is, let's say, oxygen, and then I drew this one to be, let's make them all the same. Drew this one to be nitrogen, and I drew one more to be hydrogen. But then I asked you which one of those is got the greatest temperature, or are they all the same temperature? So which one has the greatest temperature, or are they all at the same?
Up to.
So this is where, like, we kind of look at the equation. What's the average kinetic energy? The one with the greatest average kinetic energy is going to have the greatest temperature, okay? Because temperature is just a measurement of how fast the particles are moving in the air. If the particles are moving really fast, you have a big temperature. If the particles are moving slow, you have a low temperature. So the average is the peak. So here's my average for the oxygen. Here's my average for the nitrogen, here's my average for the hydrogen. So which one's got the highest average kinetic energy? The hydrogen. So who's gonna have the greatest temperature? The hydrogen. Okay. So they're not gonna ask you to manipulate this equation. They're gonna ask you something like I just said, who's got the highest temperature? And then the corollary to that one is the one like this, where they go oops. Which one's got the greatest temperature? Well, they're all at the same temperature. They all are got the same average. So if they say something like 3 gases are at 25 degrees Celsius, which one has the greatest kinetic energy? If you're at the same temperature, you all have the same kinetic energy, okay? So, once again, if you're all at the same temperature, you have the same average kinetic energy. Something else we talked about in chapter 5 is the root mean squared. The root mean squared is exactly what it says it is. It's the root of the mean of the square. And we use u, remember u and v are the same thing, velocity. So the root of the mean of the square. And in this case, u is the speed of the gas particles in your sample. So the average squared speed. And that is more predictive of how fast a gas will move or diffuse. So if I have a tube and my tube is distance d, and I release my gas particles, and I want to find out how long is it going to take for my gas to diffuse all the way across to the other side. I don't use my velocity, because like if you were like driving a car, cars go in straight lines. So if I was driving a car, I said, well, how long is it going to take me to go from here to here? I use my velocity, because cars go in straight lines, hopefully. But gas particles don't do that. They go boom, 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 boom. So it's going to take a while for all these gas particles colliding to work their way all the way down the tube. And it is more predictive to use that, the root mean squared, to predict how long it would take. I wouldn't use V, I would use the root mean squared. The root mean squared is equal to the square root of 3RTM. I won't go through the mathematics of it because we did that back when we did chapter 5. But basically, if you take the kinetic energy, you can set it to 3/2 RT, you can get this. M is the molar mass. So basically, you're saying the root mean squared, or how fast something is going to diffuse, is going to depend on its mass. How big is it? How heavy is it? And it's going to depend on its temperature. Because if it's got a big temperature, it's going to bounce around that tube and get to the other end a lot quicker. If it's got a low temperature, it's going to bounce around slower. Graham's law is where, yep.
Does M have to be in kilograms?
Ooh, good point. Yes, the molar mass must be in kilograms. And that, yes, good call. In kilograms, the molar mass in kilograms. Because otherwise it won't cancel with the units in R. Yep.
So for R, do you use 8.31 or do you use
8.31 for R. Almost always do you use 8.31 except for one, like, I'm trying to remember what chapter that was, we had to use .0821.
We use .0821 per chapter for the ideal gas law. So liters times that meters over moles times Kelvin.
You can use 8.31 for the ideal gas law. It was,
So
I thought it was the equilibrium constant. When calculating KP, I think we have to use .0821.
Is the 8.31, is that in kilopascals?
And joules?
8.31 is
Joules per mole Kelvin.
liters kPa per mole Kelvin. But this is equal to 8.31 joules per mole Kelvin. Because a liter times a kPa is a joule. Oh, sorry.
Yeah.
So Graham's law is when we say the root mean squared for gas 1, because that's the root mean squared. So the root mean squared of gas 1 over the root mean squared of gas 2 is is equal to the molar mass of gas 2 over the molar mass of gas 1. So, one thing they would like to do to you is do something like, the diffusion rate of gas B is twice as big as gas A. What can we say about their relative masses? So, if gas B diffuses as twice the greater rate of gas A, so